Since this moment on, we consider polynomials with coefficients in a field. So from now on, assume that f is a field. And we study the ring of polynomials with coefficients in F. I already told you about an analogy between this ring and the polynomial ring and the ring of integers. Now I want to tell you that the principal element of this analogy is the fundamental theorem of arithmetic. In both rings, Z, the ring of integers, and the polynomial ring, the fundamental theorem of arithmetic holds. Moreover, it is not only holds, but the proofs in these two situations are quite parallel. I will recall the fundamental theorem of arithmetic itself. This was the principal result in chapter 1, theorem 1.8, which says that every integer which is an element of the ring Z, except 0 and plus or minus 1, can be written as a product of primes in an essentially unique way our goal now is to prove theorem 4.4. Every polynomial which is an element of the ring F of X. F is a field, otherwise the theorem does not hold. Again, except constants. can be written as a product of irreducibles in an essentially unique way. So, first, I want to stress the analogy. We already can appreciate that there are same exceptions. And first of all, this is obviously same theorem claiming something very, very similar. Also, let us look at details. The exceptions are the same. These are the units there. These are 0 and units, the units. In the ring, the ring being either Z, the exceptions are 0 and the only units are plus or minus 1, or f of x. The exceptions are constants. Constants are elements of f which are either 0 or non-zero elements of f which exactly constitute the set of units in the ring. So these are same exceptions. Now, of course, it is clear from the way I put it that an analog of primes is going to be irreducibles. As we introduce the primes at a moment in chapter 1, we will have to introduce something similar which is called irreducibles in this ring, in this chapter. We started the proof of the fundamental theorem of arithmetic in chapter 1 with Euclid's lemma. In the ring Z. That was theorem 1.1. It tells us that for two integers, B is a positive integer, there exists unique integers Q and R such that A equals BQ plus R, and R is in the interval from 0 to B. I will rewrite it is either r is 0 or r is smaller than b, and bigger than 0. Now, an analog of Euclid's lemma holds for the polynomials. And this Euclid's lemma was actually key for the fundamental theorem. The rest was history. Now, let us formulate Euclid's lemma for polynomials with coefficients in a field. That is going to be theorem 4.6, which says that now we have f and g polynomials, elements of the ring, and we have g is non-zero. Not a 0 in f, not a 0 in the polynomial ring. This is the same thing. Now the lemma says that there exist unique elements now of our ring, polynomials Q and R, such that f is GQ plus R. And now we want to add the second condition. In both cases, for integers and for polynomials, Euclid's lemma is nothing but our ability to perform division with remainder. For polynomials, this is long division of polynomials, you probably know from high school. Remainder should be smaller. Well, first of all, remainder should be smaller than our polynomial g, as here remainder was smaller than b. But and the measure of how big a polynomial is its degree. So what we write here, that again either r is 0, now it is 0 polynomial, or instead of r is smaller than b, I will write degree of r is smaller than degree of g. So not exactly the same as here, but very, very similar to what is here. By size, r is smaller. I will give a proof which is not from the book. I actually proved Euclid's lemma in chapter 1 also differently than the book does that. In both cases, the book goes into detailed analysis of division algorithm So it performs division with remainder for integers. Now it's going to perform division with remainder for polynomials. I will try to avoid that much of calculations and follow same proof I gave in chapter 1. The proof starts with uniqueness. The Euclid's lemma claims both existence and uniqueness of Q and R. I will start with proving uniqueness for U. For that, I will write this with two pairs of Q and R. I will write F is GQ1 plus R1, and I will write F is GQ2 plus R2 with the condition on R assumed to be satisfied. Either R whatever 1 or 2 is 0, or degree of this R smaller than degree Gi is 1 or 2 here. What I want to prove is that they are the same. So wanted R1 is equal to R2 and Q1 is equal to Q2. We will need, for the proof, we will use exercise 12 from the book, page 94. The exercise tells us that for any two polynomials, whatever they are, degree of R1 plus or minus R2, whatever polynomials R1 and R2 are, is smaller or equal than the maximum of their degrees. The proof is very straightforward. You write the polynomials with leading non-zero coefficients, and you see that after you use the definition of addition or subtraction of polynomials, you produce a polynomial whose degree never exceeds the biggest out of the two, because no coefficients whose indices are bigger than the indices of leading coefficients of R1 and R2 may show up. If there are no cancellations, then this is exactly maximum of the 2 degrees. If there are some cancellations, it may be smaller. So from these two equalities, we subtract one from the other one to obtain that G times Q1 minus Q2 equals R2 minus R1. Now we want R1 to be, both of them are equal. You can we can see that F R1 equals R2, then G times Q1 minus Q2 is 0, and that implies, so G is assumed to be non-zero. So we know that the ring of polynomials over integral domain is an integral domain. F is an integral domain, being a field, so implies Q1 equals to Q2, because F of X is an integral domain. That was a statement proved last time. That was a corollary. I don't remember the number of corollary. Yes, that was corollary 4.3. So it suffices to prove that R1 is equal to R2, then Q1 is equal to Q2 automatically. So now we want just the first out of them, and other way around also good. If Q1 equals to Q2, let me write it. I will then Q1 minus Q2 is 0, G times 0 is a 0, then R2 minus R1, which is G times 0, the difference of polynomial minus itself is 0, and this is 0. So it suffices to get any one of them, this one or that one. Now I will assume for the sake of a contradiction that Q1 is not equal to Q2, and correspondingly R1 is not equal to R2. Then both of them are non-zero. Then in this identity all degrees are defined. This is a polynomial, they are not equal, so this is not a 0, and this is not a 0. Assume for every non-zero polynomial, the degree of this polynomial is defined as a non-negative integer. So, by theorem 4.2, Was it 4.2? Let me double check that. Yes. By theorem 4.2, we can conclude from this equality that degree g plus degree q1 minus q2 equals degree r2 minus r1. Again, all degrees are defined known of these three members of three polynomials here. The differences, or g, is 0. Now, this exercise allows us to conclude that this degree which is the maximum of the two degrees is strictly smaller than degree g, because both of them are strictly smaller than degree g. At the same time, degree is, by its definition, a non-negative integer. By the definition of degree. So, degree g plus non-negative integer turns out to be strictly smaller than degree g. This is on the left we have degree g plus something at least degree g, possibly bigger. On the right we have something strictly smaller. That is a contradiction. So thus the degrees cannot be not off just or the right and left hand side. Just let me write it this way. The equality cannot hold. And this contradiction proves that we assumed for the sake of contradiction that they are not equal. One is equal, another one is equal, if so we can assume only both of them. If one of them is equal, then another one. If q1 is equal to q2, then r1 is equal to r2. If r1 is equal to r2, then q1 is equal to q2. So for the sake of contradiction, we have to assume that both are not, both equalities do not hold, and find a contradiction that will write down the equality which cannot be true. So at this moment, we use the exercise that the degree of difference is small than the maximum of degrees. Now we have proved the uniqueness clause of Euclid's lemma. I will prove the existence again not following the book, but differently, following how I proved Euclid's lemma for integers, this one. I will follow that way to prove the existence. Now I want to attract your attention to how similar the proof of uniqueness is to our proof of uniqueness in theorem 1.1. Basically, this is absolutely same proof, with only difference we use degrees instead of absolute values. Thank you for listening. The existence is coming in the next fragment.